great responsibility. Induction isn't magic. It seems very powerful to be able to assume that P of k is true. After all, we're trying to prove that P of n is true, and the only difference is the variable here, k and n. Are we assuming that what we want to prove is true? Well, not really. We assume that P of k is true, not to conclude that P of k is true, but to conclude that P of k plus 1 is true. So we're not assuming the conclusion, we're kind of assuming an arbitrary case of the conclusion to prove the next case. So that's a huge difference. Still, you might start to believe that you can prove anything with induction. In this video, we'll cover an example where we prove something completely false using induction, some subtle misuse at least of mathematical induction. Okay, so let's consider this incorrect proof that every Canadian has the same eye color. So we're going to let P of n be the statement that any n Canadians have the same eye color. So we're going to try to prove P of n is true for all n greater than or equal to 1. So let's let P of n be the statement that n Canadians have the same eye color. P of 1 is true. Why is that? Well, if you look at one single Canadian, of course, everyone has the same eye color as themselves, so we're good. P of 1 is true. Now, let's assume that P of k is true. Now, that is, we're going to assume that any group of k Canadians has the same eye color. If we have a group of k Canadians, everyone's going to have the same eye color. So now we're going to consider a group of k plus 1 Canadians. So here I have a row of k plus 1 Canadians. Well, here's what I'm going to do. First, I'm going to break up this group like so. I'm going to look at these first k Canadians here. So I'm going to leave out one of them, and I'm going to look at this group. These should all have the same eye color because we get to assume that P of k is true, and we're looking at k plus 1 Canadians. So good, they have the same eyes. Let's take a look at, well, actually, let me use the same color. This group now, where we leave out one person from that other group. Here we have k Canadians again, and so they have the same eyes. Okay, so in fact, everyone in this group must have the same color. So that means that P of k plus 1 is true. So by the principle of mathematical induction, P of n is true for all n, meaning that all Canadians do in fact have the same eye color. Clearly something went wrong here. The problem is that the proof of P of k implies P of k plus 1 assumes something really important about this group here. How many people do we need to isolate? How many people do we need to be able to prove this? Well, we needed that guy and we needed that guy, or girl, I guess. And then that's a problem because we're assuming here that k is at least 2, but our base case here was k equals 1. So we never showed that P of 1 implies P of 2. We showed that P of k, well, so let me show you what I mean by that. We showed that P of 1 was true. Then we showed that P of k implies P of k plus 1 for all k greater than or equal to 2. That's a problem though, because that doesn't necessarily imply that all of P of n is true for all n. That's an integer, because how do we get that P of 2 is true? Well, I can't plug in a 1 here because we proved that this statement is true specifically for when k is greater than 2. That's not going to work. Okay, so there's no way of doing it, and that's the problem. If we had that this inductive or this implication here was true for all k greater than or equal to 1, then we can use this and plug in k equals 1 into that implication here to show that P of 1 implies P of 2, and we would have been able to get that P of 2 is true because we already know that P of 1 is true, which would then allow us to prove that P of 3 is true, and so on. And that's how induction works. But in this case, it did not work because we only showed the implication worked for all k greater than or equal to 2. And our base case was 1, which is not okay. So if you're showing that this implication is true for all k greater than some number like 2 or 3, your base case has to be 2 or 3 or whatever you chose there. So we really proved the wrong base case. We should have proven that P of 2 is true, but the thing is, it's impossible because P of 2 is not true. P of 2 is not true. If you take any two Canadians, it's not necessarily true that they're all going to have the same. They're both going to have the same eye color. That's just not true. But if you somehow prove that, you'd be able to prove that everyone has the same eye color using induction. Anyways, thanks everyone, and I'll see you in the next lecture.